Okay. Welcome to Keno's in the spring semester. I hope you guys are doing well. We will have our first lecture today. This is going to be a brief discussion on the general ideas that we will be going over in this class logistics, some introductions, things of that nature. Nothing too serious. And then once we get done with the lecture material, you guys will be asked to do an activity. That's activity 1. Mainly it's going to be sort of a review of what you learned in computer components and operations. Okay, so the reading that is assigned for this particular lecture is from a required text. Patterson and Hennessy are the authors of that text, and sections 1.1 and to 1.5 are the reading assignment from that book for this particular lecture. From the names that I see in the people who have joined, it looks like I know almost all of you. And for the very few that have not had me for a class yet, my name is Mahmoud Hamid. My email is listed. My phone number for some reason is also listed. My office hours are going to be virtual. They are going to be 4 hours in total, Wednesday 2 to 4 p.m. Eastern Time, and Thursday and Friday both 4:30 to 5:30 p.m. Eastern Time. So on Thursday, actually, you can think of it as an extension of the class, 1 hour after that, because we end the class at 4:20. The location for my office hour, virtual office hour, is going to be Webex Meeting Personal Room. The link to that is attached over here. By the way, these slides that I'm going over have been uploaded to Piazza site for this class, so you don't need to write these things down in a hurry. You can just download the PDF from the class Piazza page, and you have all this information handy. Okay. We have one graduate teaching assistant and one undergraduate teaching assistant who is going to be helping out during the semester with Keno's. The graduate teaching assistant is Jingpeng Hao. He has joined the class. So Jingpeng, if you want to introduce yourself, if you want to say a few words, you can do that now. We are not able to hear you. I know you are unmuted. All right, so Jingpeng is a TA. You guys will get to, right? So he is using the chat box to engage. So it looks like he has TA'd this course before. That's great news. I've not discussed. That's fine, Jingpeng. So I've not discussed his office hours yet, but soon we will come to an agreement about how he is going to hold office hours. But the undergraduate student assistant, who is Lawrence Liu, he took this class with me last year. He is going to be holding help sessions on Webex Teams every Monday and Thursday from 9 to 10 p.m. Eastern Time. And this is useful because of two reasons. One, people who are outside the country can go to these times. In China, it's 2:35 a.m. right now. So those students will not be able to attend class or be able to do the activity with some help. So those guys can go to the Webex Teams help session. And also, activities are due at midnight on class days. So Monday 9 to 10 p.m. has worked in the past, and I'm hoping that it'll work again. All you need to do to join that team is through that link or you can just go to the class, general class Webex team, and then I've created a subspace for the Monday, Thursday help session. And if you have any difficulty finding that location, please let me know and I'll help you out. So Lawrence is going to be available for 1 hour each on class days using Webex Teams. Okay. How are things going to go in terms of grading? We will have an activity on every class day. So when we were in person, the way things would work is generally I would have 1 hour lecture, and then the rest of the time during the class time would be dedicated to students working on the activity with some with help from the teaching staff. But because we are doing this remotely, we are going to have a lecture, maybe more than 1 hour time, but the rest of the class time can be used to do activities, and we will be here to help you out. But instead of making the activities due at the end of every class, they are now due at the end of the day. So 11:59 p.m. Eastern time, that particular class day. Every class will have one activity. They have been designed to be completed in a very short time. An average could be 1 hour time. But you have more than an hour to finish it, right? These are not supposed to be very difficult, although in some activities you might need some clarification. That they constitute 15% of your grade. Next, generally we are going to have one homework assignment per week. I have not assigned the first homework assignment yet. I will be posting that later in the week. They will be due every Thursday. 15% of your grade. So 15% each for activities and homework. All the things that are going to be submitted will be through Gradescope. And I'm very sure that all of you have used Gradescope before. You should be on there as well. Exams. So we are going to have 2 midterm exams that make up 40% of your grade, 20% each. And then you'll have a comprehensive final exam for 30%. How about a little bit more details regarding activities and homework? Activities must be uploaded to Gradescope by the end of the class day. Unfortunately, we will not be taking any late or makeup activities. These are assigned on Piazza before class, and many of you might have already noticed the first activity. I posted that yesterday. So you guys, some of you at least, might have already started working on it. It is to be completed today, and it is going to be due tonight at 11:59 p.m. We are going to make every effort to complete the grading of activity before the next class. And given the low number of students, I don't think that is going to be a big issue. Homework. Late homework is not accepted, assigned on Piazza, due on Gradescope, and we are going to try to get your graded homework back by the following week of submission. These are important dates, and I want you guys to note these down on your calendars. March 1st, 2021 and April 5th, 2021. That's the day for exam 1 and 2 respectively. And then the final exam, of course, is scheduled by the registrar, but it is going to be between May 6th and 12th. So please don't note them down in your calendars, and make sure that you don't schedule any interviews or travel or anything of the sort around the exam days. And as we get closer to March 1, I will be discussing the logistics for the class. I need to figure out where are you located, what is the composition of the class, and based on that, the logistics for the exams will be determined. Questions here? or so far? Thomas says, for the activity, are we expected to print out and send a scanned worksheet, or can we just write out our answer on a separate sheet of paper? Yeah, absolutely. Either option works. All right, let's move on. There are 2 required textbooks for this course, and they are available at the bookstore. And they are digital forms of the textbooks that are available. I'm not going to tell you how you get the book, but I am going to tell you that you will need the book. So make sure that you have both these textbooks. You will be using them for reading assignments or for doing homework, or as an open book, open notes situation for exams. So make sure that you have these 2 books. The first one is based on computer architecture. The title is Computer Organization and Design, from Patterson and Hennessy. Very well written book. It's been a lot of schools use this book. The 5th edition of the book is what we are going to use. For operating systems, we are going to use Silberschutz, Galvin, and Gagny, the 9th edition of the book. I think the 10th edition is also out, or maybe it's very close to being published, but we are going to stick with the 9th edition of that book. So both of these books are required texts. Again, digital copies are available. For the networking part of the course, I will be supplying lecture slides. So for that part of the course, you would not need any book. All right. We will be using Piazza and Gradescope. Piazza, as usual, if you have taken Coco with me, as most of you have, you know that I use Piazza as a one-stop shop for lecture slides, for homework, for activities, activity solutions, for homework, homework solutions, for exams. All of that I post on Piazza. Gradescope, everything that needs to be submitted and graded goes on Gradescope. Each and every one of you should be on these 2 platforms already. I checked before class started, so should be okay. All right, the Webex platforms that we are going to use. The first one is Webex meetings. We are going to use one link to access the lectures for all the classes throughout the semester, and I have put that as a pinned post on Piazza. So make sure that you look at it, maybe even bookmark that particular link, so you have you don't miss that. We will also use Webex meetings for instructor office hours. We will be using Webex Teams, and I've titled our Webex Teams for this class as ECSE 2660 Kano's Spring 2021. All the students have been added over there. The TA and the undergraduate student assistant have been added over there. And for those of you who do not know, there's a smartphone app available for Webex meetings as well as Webex Teams and Piazza. So feel free to take advantage of those apps. Also, since you guys have used Webex, I'm pretty sure that most of you, if not all of you, have used Webex Teams before. So you might be familiar with how do you create spaces within a class in order to work in smaller groups. Now, what I'm hoping is some of you might know each other from a class that was in person a few years ago, or from a class that you took remotely in the recent past. And if you know a certain group of people, ideally what I would want you guys to do is create more spaces and make sure that they are under our class and not outside. They should be under this particular title. And once you create those, the goal is for a group of maybe 6 to 10 students, or maybe a smaller group, whatever works for you, to work together, to discuss activities and so on. This is of course optional, but I think you guys will benefit from each other if you work in smaller groups. So feel free to create more spaces. Okay. How about the YouTube channels? I've created one playlist for spring 2021. No videos have been added over there yet. The first one is being recorded right now. Last year, however, spring 2020, half the semester was in person. We did not have the transition to remote instruction, halfway through the spring semester. So those videos are not available. However, the second half of the lectures have been recorded and they are available at that particular YouTube playlist if you want to look ahead. Now, I've gotten very good feedback about those videos, mainly because I cut the videos down to very small chunks, maybe 10 to 15 minute videos, multiple of them, but short videos, as opposed to 1 hour 50 minute and 1 hour 20 minute, like the full length time. So they have already been split up, and they are there. I put in a lot of effort into this. These were not recorded live. These were recorded offline. So they are slightly more to the point than what a typical lecture tends to be. So if you want to look ahead about the lectures, you can feel free to do that. Okay. Prereqs. There was already a question about this. I've taken Coco, I have not taken LITEC. What then, right? So there are several ways to come into Kainos. One is through Coco and LITEC. That's most people. Or you could have taken just Coco, which is components, computer components and operations. Or you might be from the CS department and you might have taken computer organization. So no matter where you have come from into this course, I'm going to assume that you have some background regarding combinational and sequential logic design. So we are talking about multiplexers, decoders, encoders, latches, flip-flops, state machines. So I'm going to assume that those ideas are very well formed. We are also going to rely on the fact that there's the computer organization part of things, data path unit, control unit, instruction cycle of an instruction. Now, depending on when you took Coco and with whom you took Coco, you may or may not have gone over these ideas about computer organization. Do not worry, we are going to be spending time starting from next class. We are going to spend a lot of time talking about these ideas. So for those of you who have already done it, it'll be a good review. For those of you who haven't can learn from scratch. Now in Coco, we focused mainly on these components. We looked at logic design, we looked at how do you use flip-flops to design registers, we looked at buses, we looked at memory, static and dynamic RAM, we looked at the design of ALU. Some of you have done a design of ALU using an FPGA. Now in Kainos, we are going to transition that to how do you design a modern computing system. We are going to talk about a modern processor. We are going to look at an instruction set architecture. We are going to focus on MIPS, instruction set architecture. We are going to look at how does a memory hierarchy work. Most people have heard of a cache memory and a RAM and a hard drive. What are the details about these things? How do you make memory? We'll talk about a lot of things here, but everybody wants memory to be fast, cheap, and big, right? But it turns out that these are competing goals. So how do you design a memory hierarchy in order to get the fastest and the cheapest and the biggest memory, right? So that's cache, RAM, and hard disk. But we'll go a lot more deeper into that. We'll also be talking about operating system functions, and then we will also talk about the layered layers of a TCP/IP or an OSI model in computer networks. All right, now let's talk about some great ideas in computer architecture. There are 8 of them, and this is what the book lists out. This is Patterson and Hennessy. Now, I really like the title Great Ideas because if you take some time and think about, a computer works on instructions, right, on operations. And we as humans, we also have different tasks that we complete throughout the day. And these ideas that we are going to learn in this course, whether they be in terms of computer architecture and design, or they be operating systems ideas, or they may be related to networking, it is fun to relate these ideas that are engineering ideas to something that is common knowledge, right? So your day-to-day tasks. The reason why I say this is recently my wife had to give a small talk regarding time management, and we were talking about what could you say about time management, and we got to talking about that, and we were just bouncing ideas off of each other, and we came to a very nice topic. The title was essentially to compare how do humans manage their time versus how do computers and operating system manage time, right? So one can learn from the other, right? So essentially the designers have written algorithms, essentially, the way operating system schedules the tasks is kind of, how a very, very effective human would. So for me, those kind of ideas are very appealing to learn from. All right, let's get into the first great idea here, which is to design for Moore's law. What does that really mean? Well, as you know, Moore's law says that the number of transistors on a given real estate on an IC doubles every 18 to 24 months. Now, when a computer designer goes through the process of designing a computer, that might take a long time. And by the time the computer comes into prototyping and the manufacturing stage, Moore's law would have gone ahead, right? So the IC resources would have doubled by that time. So computer architects and designers need to keep that in mind, that the IC resources are going to double every 18 to 24 months. Although, if you go online and look at all the discussion about Moore's law, there will be a physical limiting factor to this. But if you just look at the concept itself, which is to plan ahead, right? Because the IC resources are going to be doubling after a specific period of time. So computer architects need to plan for that and design their computer systems based on that. Wherever you see that particular symbol in the book, up and forward, that's exactly what that signifies, that you need to think about how do you design for the future. The next great idea is using abstraction to simplify design. And everybody does this, almost everywhere. And there can be several layers of abstraction, actually. And like the bullet says, it is to simplify design, right? So the lower level things can be very complex. Now, for example, if you think about an AND gate, right? So if you just think about AND logic gate, then you just say, all right, that is just this, right? However, that is just the symbol, right? That symbol is an abstraction that is hiding the lower level complexity. What is the lower level complexity? Oh, actually, there are many CMOS transistors that are involved in the design of the AND gate, right? So instead of actually looking at it from the transistor level, now you are looking at it in terms of a schematic level, right? That's a layer of abstraction. So abstraction is, I would say abstraction is used for two primary reasons. One is to essentially hide the complexity of the lower levels or to simplify design. And the second reason is to be able to troubleshoot easier, right? If you are layering things and if you are doing an abstraction over abstraction, then it becomes easier for you to troubleshoot where the error is in your system. And there is an abstract painting icon that the book uses for that. Next, great idea, make the common case fast. As opposed to what? As opposed to spending a lot of time optimizing the rare case, right? So when you're doing a computer system design, you want to look at common case. What is that? Common operations, common instructions that are being executed by a computer. And you would want to focus your time and energy in making the common case faster or more efficient, as opposed to looking at a very, very, rare case and saying, oh yes, that particular instruction might be getting executed at some point. Let me spend time in order to optimize how my computer executes that instruction, right? That's not a good way of doing this. Making the common case more efficient is much more beneficial. And for this particular item, we have a sports car icon over here. Like sports car commonly takes what, 1 or 2 people, right? That's common. That's why we can make that faster, hence the sports car, as opposed to a truck, for example, or a train. Takes in a lot of people, but is not that common. Let's go to the next idea, which is performance via parallelism. Performance of what? Performance of a computer. What does that mean? Performance of a computer. Well, it can mean many things. It can mean efficiency in terms of power. It can mean the number of instructions that a computer executes in a given amount of time. It can mean anything. Performance can mean anything. But you would want to increase performance by using parallelism. For that, we have a plane with 4 jet engines, right? With 1 jet engine, it won't go as fast. With 4, it can. So by doing things in parallel, you increase the performance of the operations. So it's sort of very, very intuitive way of looking at things. The next idea is performance via pipelining. And we have a set of pipes that are linked to each other as the symbol for that. Now, pipelining is, one of the ideas I really like. And in the book, the author talks about, a human chain to put out a fire, right? So imagine a human chain in which all the people that are involved are passing a bucket or are passing buckets of water to the last person in order to put out the fire, right? So that is going to be much faster than one person running back and forth between the water source and putting out the fire, right? So by arranging things in a pipeline, you are allowing every resource to be used almost all the time, right? So the first person in the human chain doesn't wait until the bucket of the water is being dumped on the fire. They are constantly working, right? So that is called pipelining. And instead of water being put on the fire, we will be executing instructions instead, right? So stages in the computer system that are going to be working on stages in the computer system that are going to be working on completing a particular instruction, right? That's the computer system instruction cycle pipeline. Very interesting idea. We'll learn a lot about this as we go through the course. Next, performance via prediction. Another very interesting idea, right? Prediction. It reminds of the phrase, it is better to ask for forgiveness than for permission, right? So you predict what the next instruction to be executed is going to be, and then you start working on that regardless. If it doesn't be true, if it is not true, if that is not the next instruction, then you can trace your steps back. That is actually better than not predicting at all and then just working on things as they come in. So by predicting, okay, what is the next operation or instruction that is most likely to get executed, you start working on that right away, right? And you increase performance on average by doing prediction. And we have a crystal ball for the prediction. Hierarchy of memories. I touched on this a little bit, right? This is the hierarchy of memories. There's essentially a triangle, right? At the very top, you have, your fastest and the most expensive memory, right? Let me just write that down. At the top, oh, too big. So you have the fast, but small, right? Memory there. And then here you have the slow but big memory here. And because this is fast, this is expensive, and this is cheap. An example could be what? A cache here and a hard disk drive over here, right? So essentially, the idea is if you have a hierarchy of memories laid out in this structure, then you can give the illusion to the user that you are in fact using a fast, big, and cheap memory. So, but for that to happen, you would have to arrange the memories in that way. Again, we will learn more about these ideas when we talk about memory. The last great idea here is dependability via redundancy, right? So we all know that things that are important to us, if they are very, very, very important, then we need to have a backup for that, right? So one tire on a tractor trailer, the second tire is a backup for that, right? So if one tire goes out, then we rush to the mechanic to get the one that is fixed, but we are able to still drive because of the second one. So by having a redundant second tire, we are able to depend on that tractor trailer. So having redundancy in certain components in your computer can make it more dependable. So those are essentially your 8 great ideas. Maybe you guys can figure out a 9th one and add to the list. All right, questions about this slide? I know I've kind of rambled on for a long time, but I'll take a moment here to take your questions. Okay. Doesn't look like you have questions now. Let's move on to looking at computer abstractions. Again, layers, right? So you will see layers in every main topic in this class. You will see layers in computer architecture. You will see layered design in operating systems. You will see layers in networking as well. Again, the goal with layers is to divide and conquer, right? So you are isolating functionality into multiple layers. And as you're going from one layer to the other layer, you need to worry about the interface between the layers. But so suppose you have a computer abstraction right here. The user is all the way at the top, right? Too small. The user just interacts with the application software. For example, the application software could be just a word processor. But all the way at the bottom here, that's where the actual hardware is, right? So how does the user interact with the hardware? Because the hardware, the computer is going to be, that is going to execute the instructions. The user doesn't know what is going on in the background. All they're doing is typing in using their keyboard and moving their mouse and so on. But there are several things that are happening that are essentially transparent, like the user doesn't even see them. For example, if you start with all the way at the top, you have your application software. What are some examples about that? Java, Python, C++, C#, all these are application softwares. That's what the user interacts with. And underneath those application software, you will find low-level system software. This can be a variety of things. Assembly language, operating system, compiler, all of those things go into this block. The user doesn't see them, interact with them directly, but the application software does. Underneath that low-level system software, you have binary microcode language. What is that? A bunch of zeros and ones. Who understands bunch of zeros and ones? Only a computer does, right? The reason why we need to worry about zeros and ones is because these are electrical signals on and off that the computer understands very well without ambiguity, right? So the binary microcode language is under the low-level system software, which constitutes the instruction set architecture, or just ISA. And every type of processor will have their own, ISA, their own data types, their own functions, their own registers, all of that. So for example, there is MIPS, which is multiprocessor without interlocked processor stages, pipeline stages. More about that later on in the course. There is RISC, there is x86. So depending on the instruction set architecture, the low-level system softwares can be translated into a different set of zeros and ones, right? But those are all going into this particular layer under the assembly language. Under that, you have register transfer language. What is that? RTL. Where have you seen that before? Well, when we were talking about basic computer organization, you guys must have heard program counter, move the contents of program counter into memory address register, right? So those are an example of register transfer language. It's a symbolic notation for denoting transfer of data from one register to the other. Under all of that, you have the digital logic, right? And then under that, you have the transistors. Digital logic comprising of Boolean algebra, state machines, combinational logics, sequential logic, all of that, right? So the user is setting up all the way over here, while the computer is working on their particular instruction, right? But they don't see what is under the application software. All they care about is how is their experience in the application software layer. But to support that, you need all the other layers at the bottom. Those are what dictate performance, overall performance. Here is an example of how the high level language needs to be converted or translated into assembly language, further needs to be translated into bits in order for the computer to work on them, right? Now, if you wanted the computer to work on something, all you need to understand is this, right? But if I ask you guys to write a program which does a bunch of interesting operations, but if I wanted you guys to write in the form of zeros and ones, you guys will have a very painful time, right? And so did the people who did this for the first time, right? Machine language was actually directly fed into the computer processors to begin with, but that got to be very painful. So the next layer came in, which is the assembly language, right? So people started writing in assembly, which is over here. So symbolic notation of instructions. The user may be able to easily write those out, and then the assembler translate that to zeros and ones, right? So that became a little bit better for the user in order to complete a particular operation. But even better would have been a high level language such as C. You write the code or your algorithm in a way that makes logical sense. A compiler that is part of the system software converts that or translates that into an assembly language that is for a specific instruction set architecture. Right here, this is for the ARM v8. This could have been for MIPS. This could have been for RISC, which is the reduced instruction set computer. So different ISAs will have a different set of codes, instructions, registers, different ones. If you don't understand all of this, don't worry about this. We'll go into a lot more detail about assembly for MIPS and the binary, the machine language in a lot more detail as we go through the first 8 or 10 lectures. But the goal is, if I write my program in C, which I could on any platform, I could use a compiler that converts it into assembly, and an assembler can be used to then convert it to machine understandable bits. That's what the computers work on, right? So when you go into the zeros and ones, that is going to be your encoded instructions, and the part of the data is also over there. Instructions as well as data is being encoded at the lowest level. But at the highest level, we have a program that is C that a user writes, which is syntax based, much easier on somebody who wants to perform a particular task. In the middle, we have assembly, which is essentially your symbolic or textual representation of instructions. Another note here, which is the high level language provides for productivity and, more importantly, portability, right? I can take this C program on any platform or on any ISA, and depending on that ISA, I will have a different assembly language and a different binary machine that particular processor understands. But the high level language allows for portability. Another thing to note here, just to give you guys a little bit of a head start on this. Assembly language, there is one particular instruction, one particular statement for every operation, right? So for example, you have add, right? That is one instruction. And if you notice, what is add corresponding to? All of that. The second instruction add corresponds to a 32-bit sequence this specific 32-bit sequence in order to do this addition operation of two numbers in this particular ISA. Now, when we actually start working on the MIPS architecture code, you will see a different set of instructions here. They are going to be similar to this, but they are going to be different. And they are going to be a 32-bit code that you will be able to translate. Right? Given an instruction, you will be able to translate to this. But if I go back here, by the end of maybe the first 10 to 15 lectures, given this, you will be able to go to that and that. That's the goal. One of the goals, I should say. All right. The layered approach in general, because we have been talking about things being layered for operating systems, for computer architecture, for networks. Like, how does it benefit us, right? The design and building of complex systems, one layer at a time, is what is the layered approach. And how does it benefit us? Well, when you make upper layers by assuming that we know about the lower layers, that allows for the complexity to be really, really high at the low level. And as you go above on the layers, the complexity can reduce, so that people that are interacting with these set of layers at the very top, they don't need to worry about all the details or the complexity of the lower layers. That's the goal, right? The second goal, like I mentioned earlier, was also to be able to easily troubleshoot if there are any errors popping up. What did we do in Cocoa? If you think about that, we went from transistors, that was our lowest level, to logic gates. Then we did combinational logic, such as a multiplexer. Then using flip-flops, we made memories and ALU and state machines. We did not worry about transistors when we were looking at state machines, right? We worried about transistors only when we were talking about logic gates. The moment we went into multiplexers, we stopped thinking about transistors, right? So that's the idea. You build on top of those layers to hide complexity. For operating systems, the layers are slightly different. All the way to the bottom, that the user, the closest to the operating system is your system kernel. And all the way at the top is your user interface, the GUI or maybe the command line interface that the user interacts with the operating system. That is over here. And underneath the system kernel, that's actually your hardware, right? That's your computer. That's very close to the actual instructions getting executed physically. But in the middle, there are several layers. A layer for file management, a layer to control, manipulate, move data between I/O devices, such as a keyboard, mouse, a monitor, a hard disk. Underneath that, you have your memory management, cache, RAM, secondary slow hard disk. All of that goes in that layer. And under that, you have your system kernel supporting system calls. Under that, you have your hardware. So again, operating system has layers. More about these when we go into the OS related topics. For networks, we have a bunch of layers too. All the way at the bottom, you have your physical layer. An example of a physical layer is what? A wire connecting two things that are trying to communicate with each other. For example, if you have a wired Ethernet connection, that connection itself is the physical layer, right? So that's actually the something that's hardware. Well, in the case of wireless transmission, then you're thinking about the wireless medium between the transmitter and the receiver. That would be your physical layer then. It could be an optical fiber. That could be the physical layer. So all the details and engineering and the design of those things, they fall under the category of the physical layer in a computer network communication. Above that, you have the data link layer that takes care of error control and MAC, media access control. Above that, you have the network layer that is responsible for packetization, addressing, and routing of a frame from the source to the sink. Now, these three things are kind of more important than the two above that. The reason is, from point A to point B, no matter how many routers you have in the middle, everything looks at this, right? So you need the IP address, some of the things that you need, IP address you need, right? And then you need the MAC address. And then you need what? The port number for a computer to communicate to the other computer. All these things go here, right? So IP address falls under here. The MAC address falls under here. The port number falls under here. So these three things, every router between the sending computer and the receiving computer, or I should say device, because now computers are everywhere, right? Everything sees those things. But things that are above that are not seen by the routers in the middle, right? The transport layer, which is used for end-to-end connectivity, flow control, and the application layer itself, email, web browser, all of that belong to the application layer. The routers don't see the top two layers, they only see the bottom three. And in fact, if you look at a particular type of model, there are two of them. The first one is the OSI model, the other one is the TCP IP model. Depending on which model you are looking at, these might be slightly different. But generally, you have these 5: physical all the way to the bottom, application all the way to the top. A fun exercise that you guys can do here is try to look at the number of computers around you, number of processors around you, right? Just try to calculate. You will see one or multiple actually in your car, right? You will see one sitting on your desk, your laptop, multiple cores actually on that one. Your phone, your smart home appliances, you can go on and on and on, right? So computers are sort of everywhere, even though we don't realize it that much. And to some degree of complexity, they are all addressing these ideas. Okay, let's move on here. All right, so we'll stop with this, and then now I would encourage you guys to do a few things. One is activity 1. I've posted that on Piazza, so grab the file from there and you can work on it. I will be here in the Webex Teams room, and I will also be monitoring the Webex Teams chat. You guys can work on either platform. This is essentially a review of Coco, so I'm not concerned about this. I think most of you will be able to finish it, but in case you have any questions, please feel free to ask here or on the Webex Teams platform. You need to upload the completed activity to Gradescope by 11:59 p.m. Eastern tonight. There are 2 more forms that I want you guys to download from Piazza and upload to Gradescope. They are due February 1st. So you have Feb 1st? Yeah, Feb 1st. So you have 1 week to do that. One is an acknowledgement that the class is using the digital tools such as Webex and Piazza and YouTube and all that. And the agreement to the academic integrity policy for this class. So please read these forms carefully, sign them, and upload these forms as soon as possible to Gradescope. It shouldn't take you more than 5 minutes to do the signing and uploading, and reading can take a bit of time, but it's not a particularly lengthy process. So I would encourage you guys to do this and work on activity 1. I'm going to stop the recording now.